And we're recording. So, hi everyone. Thank you for coming in. Hi Chu-Cheng, thank you for coming in. Everyone, this is Chu-Cheng Lin. He just defended his PhD at Johns Hopkins, and he is here to tell us about one of his results about the limitations of autoregressive models and their alternatives, and basically the difference between predicting something token by token as opposed to predicting something right at the end of a sequence just after seeing the entire thing. I think that's reasonable.
Yeah, it's pretty, yeah.
So take it away.
Okay. So hello everyone. I'm going to present the paper limitations of autoregressive models and their alternatives. This is joint work with Aaron, Xin, Matt, and Jason. So the presentation is largely adapted from a previous NICO presentation. And please ask any questions if you feel confused or just want to ask questions in the middle. Okay, so in NLP, there are two popular model architectures. The first one is autoregressive models. They are widely used in language modeling and many C2C applications. The second one is energy-based models. For example, if you have a BERT model and you fine-tune it, you can call this an energy-based model. So in this talk, we ask the question whether the two are equivalent in expressiveness. One of our main results is no, energy-based models are strictly more powerful. In this talk, we will also see how model families that are more expressive than autoregressive models must make their own trade-offs for expressiveness. So we will firstly briefly review autoregressive models, and we will explain why they are weaker than energy-based models. So many NLP tasks require comparing the goodness of different strings. So for example, you have language modeling, and in machine translation, you can just, like one way to view machine translation is like to compare the goodness between different string pairs. So to compare the goodness of different strings, this is often done using neural networks in practice. So when we fit different strings into the network, we will get different scores. And then we train the network to approximate our scoring function. We regard the non-negative network output as a goodness function of the inputs. The network can usually be evaluated in polytime in the input sequence length. We also define the support of goodness to be the set of strings whose goodness is greater than 0 here. We often want to score the goodness in an absolute sense. This will allow us to compare goodness between different models. Conventionally, we normalize the goodness to a value between 0 and 1. In this case, the goodness function is a probability mass function. To normalize goodness scores, we need to compute the partition function z, which is generally intractable. Fortunately, there's a subclass of energy-based models that allow efficient computation of normalized goodness scores. In other words, they define probability mass functions directly. Such models usually have a softmax layer at the top of the network, and they define conditional probabilities over all types in the vocabulary. For example, to get the score of the string roses are red, we will first fit in the string star symbol and get the conditional probability of the word roses. And then we fit roses into the network and get the probability of R, then red. So we take the product of all these conditional probabilities as the goodness score of roses are red. More formally, an autoregressive model takes the prefix as input and defines conditional probabilities over all possible continuations. All these conditional probabilities can usually be computed in polytime of the prefix length. Since autoregressive models factorize a normalized distribution into a bunch of factors, the partition function is guaranteed to be 1 if the model is consistent. So we don't need to normalize again. We can also sample from an autoregressive model easily, but we cannot really do so for energy-based models. We said earlier that autoregressive models have to give up expressiveness for such convenience. And in fact, in this paper, we also identify some other model families that are strictly even more powerful than energy-based models. in terms of the language classes of the supports. In other words, the model class we obtain by having a polling layer at the top of BERT is going to be stronger than that of GPT-3. And again, we identify some other model families that are strongly more powerful than energy-based models in terms of the language classes of the supports. So we want to share some intuition why energy-based models are strongly more powerful. Suppose we want to model a formal language where the strings are of the form formula followed by assignment, where formula is a Boolean expression and assignment is a Boolean vector. We require the goodness function to be greater than 0 if the assignment satisfies the formula and 0 otherwise. We can show that such a goodness function can be implemented as a neural network. But on the other hand, can we implement this goodness function using an autoregressive model? Computing the first token right after the encoding is hard because in general, we need to consider all possible continuations, even just to decode the first token. For example, the probability of A1 equals 0 given the formula has to be small or 0 if there are few or no satisfying assignments that have A1 equals 0. And there are exponentially many possible continuations. So converting this huge branching tree to an autoregressive model will take a lot of computation. And we simply cannot store all the pre-computed results in a fixed size model. On the other hand, energy-based models do not need to check all continuations. They just need to ensure that they can score a single one. In other words, energy-based models do not need to know how to compute the partition function. More formally, we can show that computing the conditional probability of the first bit is NP hard. So there's no polytime autoregressive model that can model such conditional distributions if P is not equal to NP. We are actually able to show some stronger results. There are distributions that can be captured by energy-based models, but no autoregressive model can capture such distribution exactly or approximate them well enough to get the same ranking of strings, or even approximate within any multiplicative factor. So here, a question will be, why should we care if our data sets are finite? In other words, we should be able to make the model just larger if a smaller one doesn't work, right? So basically, an argument is that if some finite size autoregressive models are not powerful enough, then we just increase the size to make them more powerful. Like this, specifically the setup will be to train models of different sizes for different problems. So for easy or short problems, we will use a smaller model. And for hard or longer problems, we will use a larger model. So theoretically, if you want to memorize everything, you can just store finitely many answers in each model. And for harder problems, you will just use a bigger model for it. This will work if you are willing to have your model size grow exponentially in input size. But assuming that NP is not a subset of P/poly, these are both complexity classes, and that your model size only grows polynomially in the input size. And namely that if you don't want to just memorize and you actually want your models to learn something deeper, then autoregressive models simply cannot do that. There will be problems that these slow growing autoregressive models can never capture. So, okay. Now, you may also ask, why should I care about Boolean set problems? It turns out that autoregressive models in general cannot capture distributions over strings of the form problem followed by solution, where problem is computationally hard to solve. And many computational linguistic problems are computationally hard. For example, parsing of many formalisms, propositional logic, which is crucial for general logic inference, and optimality theory, etc. So important linguistic regularities will not be able to be captured by autoregressive models. We wanted to talk about propositional logic as an example, but that'd be boring. So we will talk about Star Wars as our example instead. So let's assume that we have a really, really powerful autoregressive model that's called GPT-3PO. And it's a really, really good storyteller. So he's going to tell us a story from a galaxy far, far away. So a long, long time ago in a galaxy far, far away, the rebels fought against the Galactic Empire and eventually won. So the story started with Luke. Assuming that the story GPT-3PO tells us is the Star Wars story, then there will be a point where Vidar, who is the bad guy here of the story, says to Luke, our rebel hero, that, look, I'm your... Now, our GPT-3PO, our language model, has to finish the conversation. Could the next word be friend? Since I'm your friend appears to be a frequent foreground, that could be a plausible choice. So Vidar and Luke become good friends and they enjoy their friendship. And since Vidar is a bad guy in the movie who wants Luke to be also a bad guy, he will turn Luke to the dark side. And that doesn't go well with our assumption that rebels won because the rebels will have lost this way. And here's another word choice, father. Father is indeed the observed answer. We note that it was decided that Vidar to be Luke's father even before the movie production. In other words, humans use look ahead to decide that the word should be father here. And we now get to an ending where the rebels won, following this line. So the continuation "I'm your friend" sometimes doesn't result in an ending we want because of inconsistencies with earlier parts of the story. We want to know if we can tell such inconsistency as early as possible. In other words, we wonder if we can learn the conditional probability of friend should be low. It turns out that we can't. Moreover, on the smooth distributions that assign probability mass to every string, no autoregressive model can assert that an inconsistent continuation will have lower probability than a consistent continuation, even when both continuations are of similar lengths. A brief summary so far is that we see autoregressive models cannot even guarantee that the generated continuation is consistent in the propositional logic. This is bad because checking the inconsistency is easy. Speaking very, very loosely, autoregressive models cannot tell between a surprising plot twist and an inconsistent continuation. So, okay, do I have any questions so far regarding, I don't know, like Star Wars or whatever? Or should I just move on?
Do you mean to say that, in a sense, when the model, should the model have continued to predict by force all the way to the end and say Luke and Darth Vader were friends and so they didn't fight and the bad guys weren't defeated, then had it gone all the way to the end, it would have been like, hang on, this is bad, I should have given it probability 0 and I will give it probability 0, but I should have stopped all the way back and I didn't realize that when I was back there.
Yeah, so basically, because evaluation, like you are forced to generate the next token under autoregressive models, and that limits your capacity to assign very low probabilities to for your next conditional, like for your next token in the conditional probability assignment. So
But if I may argue with you here, just for the sake of understanding, if the probability of friend and the probability of father were approximately equal at that point, one because it was quote unquote wrong and the other because it was a plot twist, that means that overall the total probability mass for those continuations is equal. Do you mean maybe that all possible continuations from the friend point are extremely unlikely, whereas there exists one rather likely continuation from the father point, and we don't know to discern the two cases?
So are you saying that if the true probability of the friend and father should be equal? Okay,
then,
so if
then
the
who's
true
to say it's wrong?
Yeah, so in that case, like because we do the reduction to set, so we only consider the case where the difference is very large, like where on one branch you have 0 or very little probability mass, and on the other branch you have like a huge probability mass, almost 1. And we can show that in this case, autoregressive models cannot do assignments accurately. But in your case, when they are equal, then yeah, we don't know. Like this is not covered by my results. So maybe autoregressive models can do this very well. Yeah, maybe. Yeah.
Okay.
Yeah. Okay. All right. So I'll move on. Okay. So now we'll look at alternative model families that are more expressive than autoregressive models. So first, we review our progress. We said that autoregressive models are appealing computationally wise because they evaluate strings scores fast. They are also easy to sample from. And the big downside is that they are not powerful enough to capture all the decision problems in P. So we also show that it's not like P. We can fix the problem by throwing more parameters, unless we have a lot of parameters, or unless that the complexity assumption we assume is false. We also look at energy-based models. They are slightly more powerful than autoregressive models. They correspond to the decision problem class P, because each energy-based model is essentially a polytime algorithm. Evaluating string scores is fast because it's polytime, and the number of parameters do not need to grow fast to stay expressive. However, there's a downside that sampling from them and parameter estimation can be more difficult or impossible. We know that there are many different decision problem classes. We talk about P, and we know that there's something called NP, right? So for example, do we have some other family that can correspond to this class NP? So there's actually one that's called autoregressive latent variable models. Basically, if you have latent variables, then you can be very powerful, even though when you are still autoregressive. Okay, so here's another Star Wars example. In previous example, we say that autoregressive models may not prefer plot twists like "look, I'm your father" to other more bland but logically inconsistent continuations. But actually, autoregressive models are capable of generating such plot twists. It just needs some backstory to help it justify the climax building. In other words, we will need a backstory such that the plot twist feels like a natural continuation, and there happens to be one for Star Wars. In our galaxy, the story started with Luke, and we only came to know that there was a backstory some 20 years later in the new movies. But suppose that GPT-3PO tells us the story where the backstory comes first, namely that the story starts with that in a galaxy far away, how Vidar became Vidar, and also Luke's father. And under this story, we don't need to look ahead to see what the plot twist makes sense. Actually, we can just look behind to prove that Vidar's not lying, because we are only interested in the last story. So the three previous stories can be regarded as latent variables. And it turns out that with the latent variables, even autoregressive models can do propositional logic, and they can in fact model any NP language. So as a model family, it contains sequence models where some of the symbols are marginalized out as latent variables. We can show that they can capture all problems that are in NP. So unless P equals NP, the models are actually stronger than energy-based models. They are also easy to sample from because they are just autoregressive models. And the parameter count doesn't have to grow super polynomially, so they don't just memorize. However, the downside is that even evaluating a single string weight will require marginalization, and that's going to be expensive. So again, is there anything out there? Okay,
could you explain how this looks in practice, this latent variable, if you're recognizing something like satisfiability?
Okay.
The input has a hidden part. What is it?
So basically, you will just simulate a non-deterministic Turing machine like the traces as latent variables.
You will what?
You'll have the trace of the traces of a non-deterministic Turing machine as a latent variable. And if you if that traces result in health, then you have you put some observable special token, and if not, you also put some special token. So this way you can reduce you can reduce the deciding any NP problem into computing the marginalized probability of some marginalized probability where the latent variables are all marginalized out. So so the short story is that you will have another formal language where some of the symbols are regarded as latent variables. And so go ahead.
So it's sort of like a non-deterministic autoregressive model, because it has to receive the trace in order to decide, and then only if one of the traces is good.
So the Turing machine that is being simulated is non-deterministic, but for every trace you observe, it's computing the probability of every string that has a part that has the trace as a part. Computing that is deterministic and can be done in polytime.
Yes.
Well, I mean,
so you
and you
always
can
only give the result for a single trace. Okay.
Yeah, and you marginalize that out. So thank you. This is more technical. So all right, I'll go ahead. So if you want to memorize everything, any possible results using autoregressive models, you can do that. It's just you may have to use larger models for harder problems or longer strings. But if you are committed to that, then sure, this is a better way to model stuff. And if you do that, then this becomes what we call lookup models. We know that there are certain classes of autoregressive models that have access to external knowledge. For example, the KNN, LM, and semi-parametric language models. And the factoids will conceptually be stored in a database, and you just look up them at runtime. And there are some linear time retrieval methods for doing that. And the nice thing about having this is that your model size, if you don't have any limitation on your model size, then you don't suffer any of the evaluation or sampling problems. They're both fast because they are essentially just autoregressive. But again, the downside, the obvious downside is that your model size may blow up pretty fast. But again, that may be manageable if you want to just do engineering stuff. So here's another view of the model space in a table. So if we consider the companions, then autoregressive model, energy-based models, and autoregressive latent variable models, they all check this column, but the lookup models do not. And if you consider efficient scoring of a string, then autoregressive models with latent variables, they do not check this because they need to marginalize. And finally, when you consider sampling, then energy-based models cannot easily be sampled from, at least exactly. So they all have their problems. But if you consider the support of the languages, then they're all different. The weakest is the autoregressive models. And if you do energy-based models, then you get stronger. But and autoregressive latent variables, they're actually stronger than energy-based models. And you can think of this because they are more expensive, because evaluating the string weight is expensive in autoregressive models with the latent variables. So it kind of makes sense intuitively that they are powerful. And of course, if you can memorize, then lookup models are the most strong here. Okay, so yeah, this is a high-level view of my paper. We show that autoregressive models are inherently limited. We show that unless they use superpolynomially many parameters or superpolynomially long runtime, they will not be able to deal with certain easy distributions that non-autoregressive models can. We also introduced 3 alternative model families that have strictly more expressive power than autoregressive models, but each of them comes with their own trade-off. And in this paper, we only discuss model capacity. And in our next paper, the ICLEAR paper, we actually discuss, although energy-based models can be stronger, parameter estimation can be very difficult or even undecidable. So yeah, hopefully for next time. So okay, so this is the end of my presentation. So yeah, I'm probably going very, very fast. Yeah, any questions like you would like to ask?
Thank you. That was really nice. What do you mean by parameter estimation? The amount of parameters needed for different difficulties?
Oh, just like MLE, like training models.
Mm-hmm.
Yeah.
Okay. Yeah. So it's about the learnability.
It's not like the pack learnability line is like given like a limited amount of training data, can you learn a reasonable data in finite time? And the answer is no for a huge class of models.
Oh,
because models. Yeah, go ahead.
No, could you give an example?
So for example, if you have like energy-based models, if you have like transformers, then and suppose you don't want to do training yet, and you just want to do model selection. Suppose you have like 2 parameter factors of energy-based models, and suppose you could do model selection, then you could reduce health to deciding which of the parameters is better, because and like again, if you regard the how should I say, if you have the Turing machine traces as your formal language, then you can reduce deciding whether this Turing machine helps into computing the partition function of an energy-based model, right? Because you just assign a large probability mass to traces that result in health and a small probability to traces that do not health. So if for this Turing machine, there's no trace that helps, then you know that this machine doesn't help. So if you can compute the partition function easily, or even possibly, then you'll be able to decide health. So yeah, so along this line you can show that if you can decide which model performs better on a finite amount of training of validation data, then you also be able to decide health. Okay. Yeah. So yeah. So yeah, again, so in this work, in this current paper, we are talking about a lot of reductions from set to computing conditional probabilities. And in that paper, we'll talk about reducing health to computing the partition function. So yeah.
I really like this idea of using these sort of classic results from computability to come to these models that are being used in this very common way and say, actually, this way of using a model is inherently restricted. Yeah. It's quite interesting.
Yeah. So I feel like this is an obvious topic that people for some reason didn't really discuss. Like people don't talk about like how you would do parameter estimation, but people have like a very good and sophisticated estimation algorithms. But if this is not possible for certain model families, then maybe you should first look whether you should be doing this like before you even start doing machine learning. So yeah. So yeah, we're trying to start that discussion in that paper.
Right, but on the other hand, it's like, nevertheless, these models do so much better than anything else that we've ever seen before. And like, even if theoretically it's not grounded, they seem to do quite well empirically. You know?
Yeah, but I mean that depends on what you mean by empirically, right? Because like if model selection is impossible, then how can you formally show that model A is better than model B, right? Right. So I mean, but again, empirically on like some finite time approximation, they may just do well. Yeah. So yeah, that is certainly true. So yeah. All right.